All right, so last time we started talking about the hyperfine splitting. So again, hyperfine splitting is a small correction to the energy states, primarily the ground states of the hydrogen atom. So again, if this is my, say, proton, and this is my electron. So again, the proton has a magnetic moment. The electron also has a magnetic moment. So basically, this hyperfine splitting, again, is the interaction between these two magnetic moments. So it's the magnetic moment of the electron in the external magnetic field generated by the magnetic moment of the proton, which gave us then our Hamiltonian. And where we finished off last time was then looking at the matrix elements of our Hamiltonian. So this is our matrix element. So this is any general matrix elements where I and J are two different things. And what we found was this was equal to A, which again is some phenomenological constant, which has units of energy, times then this stuff, right? Oops, go back. That's not what I want to do. There we go. So as I mentioned last time, so let me try to move all of our faces just a second. There we go. Here we have off diagonal terms and diagonal terms. So the first two terms were the off diagonal terms. We'll talk about what terms that these are in a second. And then this one is the diagonal terms. And this is the diagonal term because when I is equal to J, what happens in that case is then what? This Kronecker delta function is going to go to 0. So is this one, and this one. So these are the only two Kronecker delta functions which are going to still remain when I is equal to J, because that means that M1 is equal to M1 prime and M2 is equal to M2 prime. So from here, then we get the diagonal term of 2 times A times M1 times M2. But remember here, we're dealing with spin 1/2 particles. So remember that for spin 1/2 particles, M1 and M2 can be equal to plus or minus 1/2. So basically what that means is that this is going to be plus or minus 1/2. This would then be plus or minus 1/2. So if I multiply this by plus or minus 1/2 times plus or minus 1/2, that's then plus or minus 1/4. And then the 2's are going to cancel, which means that our diagonal terms then are going to be either plus or minus A over 2. So if we're looking at our 4x4 matrix here, so in this case, we're going to have this term would then be A over 2. And then I'm not worried about the rest of the terms. The next diagonal term is going to be negative A over 2, because remember this one is with ZZ. This one is then with Z negative Z. This one is then going to be minus A over 2, because that's going to be negative Z with Z. And then finally, this one's going to be negative Z. So that's going to give me a over 2. So my diagonal terms in this case of my 4x4 matrix are then, again, plus or minus A over 2. So the off diagonal terms, basically what this is saying then is I need to have what? For the prime then has to increase by 1 and then have an inner product then between the two of those, right? Simultaneously, so this is for the first particle. For the second particle then, what has to be true is that what? The M value for the second particle has to decrease by 1. And then I have to have a non-zero inner product between those two. Simultaneously for this one, I then have to have the Z components of M, or for the first particle, decrease by 1, and then have a non-zero inner product. And then this one has to increase by 1 for the second particle, and then have a non-zero inner product. So basically what this means then is what? For this one to be able to increase by 1, the only way that this is non-zero that we start off with is if it goes from negative Z to positive Z. And then I need an inner product then with Z and Z, right? But simultaneously, this one has to start off as Z and then go down to negative Z because it has to decrease by 1. And if it started off as negative Z, it would decrease to what? Nothing, because I have nothing below that. And then I have to have an inner product then with a what? Minus Z with a minus Z. So let's kind of write out that first term. So the delta M1 prime, that was plus 1, right? Yeah. Delta M2 prime minus 1. Well, again, what has to happen is this term here has to go from a negative Z to a positive Z. And then this term here has to go the opposite, has to go from a Z down to a negative Z, right? So that means that the only two terms or the only one term that's going to actually satisfy this is what? So this is for particle 1. This is for particle 2. So in this case, the only term that this is going to be true for then is what? So the state that's going to be a minus z with a positive z. So this is going to be my particle 1 state. Erase that bar there. There we go. And this is what was equal to what we said 3. While this one then has to what? Start off with a negative z and then go to a positive z. So in this case, I then have to have, let's see here. Did I write that wrongly? I think that's fine. So this one then has to be the 2 state, right? Which was then equal to z minus z. Okay. Simultaneously, the other term, which is then delta m1 prime minus 1 times delta m2, delta m, oops, sorry, not delta, m2 prime. There we go. M2 prime plus 1 is exactly these 2 states, just in the opposite order. Right. So basically these 2 states correspond to the same thing, which means the only off-diagonal terms that we can have are between the 3 and the 2 states. Right? Everything else has to be 0. So now if I look at my Hamiltonian, so let's talk about our Hamiltonian. So again, in our how do I want to write this? Good. So this then was going to be equal to what? Negative, or a over 2, right? And then I had a negative a over 2. Then I have a negative a over 2. And then I have an a over 2. Oops. Next. Where did all my terms go? There we go. So this one then has to be 0. This has to be 0. This has to be 0. This term is then simply going to be a. 0, 0. This term is going to be a. 0, 0, 0, 0, and 0, right? So this is then my Hamiltonian in the 1 through 4 representation. This is then H in the 1 through 4 representation. Right? Good. Guys doing okay? And again, that just comes from the facts on the previous page. So let's go back to the previous page. Where did all this stuff write down? Oh, I went backwards. Okay, fair enough. So this comes from the fact that again, 3h times 2 inner product is then a over h bar squared times then minus z s1 plus, I'm sorry, s minus 1, there we go. Keep my terms straight, s2 plus times then z minus z, right? So here, each one of these guys gets an h bar of 2. So basically this is then just going to give me a, right? And again, the other term is just going to be the complex conjugate of this guy. Right? So that's where this comes from. So good. So this is our Hamiltonian. So basically from here, we then want to what? Find out what are the energy eigenstates and what are the eigenvalues for this particular Hamiltonian. So to do that, we have to do the same thing as before. We then have to say that what? Our Hamiltonian, acting on then the state psi, or in this case, our energy eigenstates, then must be equal to the energy times then the eigenstates. Or that is E again. So, or in matrix representation, this is then going to be that matrix we wrote down. So a over 2, 0, 0, 0, and then I get a 0 minus a over 2, a, 0, 0, a minus a over 2, 0, 0, 0, 0, a over 2, times then the inner product between 1 and the energy eigenstate, 2 and the energy eigenstate, 3 in the energy eigenstate, 4 in the energy eigenstate, and all that has to be equal to the energy times then, again, that inner product. So 1 energy eigenstate, 2 energy eigenstate, 3 energy eigenstate, 4 energy eigenstates. Good. Now, again, for this thing to, as we talked about before, have a non-trivial solution, what has to be true is when I subtract this guy over here, then the determinant must be equal to 0. So as long as the determinant is equal to 0, in that case, then we can have a non-trivial solution. So let's look at that guy. So I get an a over 2 minus e. Let's put a 0 here. This term then is going to be a negative a over 2 plus e. So here I'm just factoring out that negative sign. Let's look at this term. So then this is a negative a over 2 plus e again. And then a over 2 minus e. And then this is 0, a, 0, 0, 0, 0, 0, 0, 0, 0. Too many zeros. There we go. So the determinant of this guy must be equal to 0. All right. Again, for this thing to have a non-trivial solution. So good. So take the determinant of this guy. So we'll do the usual things. So I'm going to cross off this row here, which means I'm going to multiply everything then by this determinant from here. Okay, so this is our first term. So this is the 1, 1 term. So this is positive. And then I have to take the determinant of this minor matrix. But to take the determinant of this minor matrix, what I'm going to do in this case then is I'm going to cut off this row and this column. So that way any other row that I try to multiply by will automatically give me 0. So I'm going to get this term times times then the determinant of this minor matrix. Okay. Now, since this is the 1, 1 term and this is the 4, 4 term, both of those two terms are positive. So this is going to give me a over 2 minus e quantity squared times the determinant of the minor matrix here. So in this case, I'm just going to take this guy times this guy minus this guy times this guy. Right. So that's then going to give me a times. So now I'm going to get a over 2 plus e quantity squared minus a squared is all equal to 0. All right. Guys doing okay?
So far.
Good. So now we have to determine where this thing is equal to 0. Well, this thing is equal to 0 when this thing is equal to 0, right? Or when this thing is equal to 0, right? So here, let's look at this one first. So this one says that what? This is equal to 0 when the energy is equal to simply a over 2. But since the square here, I have actually 2 of these values. So I have times 2 of this. Right? Now let's look at this term. So this term then says that this thing is equal to 0 when all of that is equal to 0. So let's square this out. So it's going to become e squared plus a squared over 4, right? Plus 2e times a over 2 minus a squared is equal to 0, right? Did I do my math right? I think I did. Okay. Good. So let's look at this guy. So here, so what's going to happen from here? So what? This 2 is going to cancel this 2. And then here, I'm going to get what, an a squared minus, or let's see, a squared over 4 minus a squared. So this is actually going to give me an e squared plus e times a minus 3/4 a squared, right? Did I do bad math in my head correctly?
I believe so, Professor.
Okay, good. I like doing bad math in my head correctly. Yes, my son.
Did you know that if I eat a type of meat, I'll be so fast and I'll be the fastest one in the house. But if I eat broccoli, I'll be so smart. I'll be able to make a big puzzle in one whole piece by myself.
Wow. Cool. All right, we'll go eat some broccoli then.
Well, I'm gonna have the broccoli after my pizza.
Fair enough. Okay, let me teach my class and then I'll order the pizza. Go.
Okay, but next time we have a pizza, I'd rather have a broccoli pizza. So
you want broccoli on your pizza?
Yes.
That's very Californian of you. Okay.
So that I can be very smart and I can eat some pizza.
Okay, sounds good. No, you can't have pepperoni. Good. So this we have to solve a quadratic. So solving a quadratic in this case, when we have minus a, because that's our b term, plus or minus b, which is minus a squared, minus 4 times a is simply 1, times c, which is 3/4 a squared. So this 4 cancels out this one. So I get in here. So that gives me an imaginary term. Why is that imaginary? Do I have a negative sign wrong somewhere? I don't think so. All right, well, let's just keep going. So this is then going to give me a minus a, let's say plus or minus. So this is going to give me a, where did I go wrong? Did I multiply something wrong here? No, that's right. Good. All right, so this then should be equal to, let me write it out. So this is going to be equal to what? A over 2 and minus 3a over 2. So these are the solutions I should get. Let's see here. So where did I go wrong? Good, so I got that guy. Okay, let me check here. So squared, good. What's that guy squared? Plus the cross term, good. That's fine. 2 times a over 2, good. So e times a minus 3/4 a squared. No, that all looks right. I copied that down right here. Yeah. So e squared plus, so I get minus a minus 9. Oh, minus a minus. That should be a plus. Okay, good. Good, good. Where were you guys? You're supposed to tell me these things. Okay, so that's 4. So this becomes good. So this is going to be the square root of, so I get 3. So that's a 4a squared. Good, all over 2. Good. So I can fill in my gaps here. So let's keep going. So this is then equal to minus a plus or minus 2 times a divided by 2, right? Good. So if I subtract them, then that's going to give me a minus 3/2 a, good. And if I add them together, so that's going to give me a over 2. Good. So those are my 2 solutions. Good. Knew it didn't round right. Okay. Good. So basically, if we compare that to, again, our other solution, we already had 1 solution or 2 solutions for a over 2, which means that our eigenvalues that we have in this case, so our eigenvalues then are going to be equal to a over 2, but I have 3 of these, and minus 3 over 2. Okay, so these are my eigenvalues, which basically means that our energy, which is equal to a over 2, is then what we call threefold degenerate, because they are the same. And then our energy, which is then equal to minus 3 over 2, is then non-degenerate. Right? So this is non-degenerate. Good. So these are then our eigenvalues. So these are the energies then for these allowed states, which basically means then what's going to happen then is the hyperfine splitting then is going to split the ground state, where E1 is equal to the ground state energy. So what happens then is that what? The ground state energy then is going to split up into 4 different energies, where 3 of them are actually the same. And then this one is going to become now the new ground state. So this non-degenerate case is now going to become the ground states. So what that means then is, if I think about the energies, so if this is the energy, so initially this is the ground state energy E1. This then is going to split into 2 other states, technically 4, but let's say 1 here, where this has an energy of E1 minus 3a over 2. So that's the energy for this guy. And then this is going to increase the energy for these, which is then going to be E1 plus a over 2. Right? But again, this one is threefold degenerate. So what happens then, again, in the hydrogen atom, because of this interaction then between the spins, basically of the electron and the proton, the ground state energy then splits up into 4 different energies, where again, 3 of them are the same, 1 is different, and that 1 now becomes the new ground state energy, and the other ones now become an excited states. Okay, so this is now my new ground state energy, and these are now in excited states.
Daddy, Marshall has a cut.
You got a cut?
Can you fix him?
Oh, he's broken. I'll do my best. I'll get the glue later, okay? Guys, okay? So the next thing we want to know is what are the eigenstates then that correspond to each one of these. So let's go back to our matrix. So now we have a over 2 minus e, right? Then we have 0, 0, and 0. Then we have a minus a over 2 plus the energy. And then we have an a here. Good. And then a 0 and a 0. Here then I have a minus a over 2 plus e, a, 0, 0. And I got 0, 0, 0, a over 2 minus the energy, okay? And then I need all of that times a times b times c times d is then equal to the 0 vector, right? So here I'm just writing that a is the inner product between 1 and the energy eigenstate. B is the inner product between 2 and the energy eigenstate. C is then equal to 3 energy eigenstates. And then finally, D is 4 energy eigenstates. Okay. So good. So let's multiply these out. So the first one here simply tells me that what? A over 2 minus E times A must be equal to 0. So that's my first equation I have. The second equation tells me that minus A over 2 plus the energy times B plus A times C must be equal to 0. The third equation then tells me that what? A times B minus A over 2 plus E times C must be equal to 0. And then finally, I have A over 2 minus E times D must then be equal to 0. Guys doing okay?
Thanks.
And we'll talk about all the scrap means in a little bit. Guys okay?
So far.
Good. All right, so let's look at then our energies. So first, let's look for when the energy then is equal to what? Minus 3 over 2. So let's look at the non-degenerate case. So in a non-degenerate case, all that means then is what? This guy is going to be non-zero, right? This is going to be simply 2a. So I have 2a times a must be equal to 0, which means a then must be equal to 0. Right. In this case, I then have what? A over 2 minus then a 3a over 2, which is then equal to what? A negative a, right? So then I have negative a times b plus a times c is then equal to 0. This one tells me the same thing. So I have a times b plus, minus a times c is equal to 0. So these two things are redundant, tell me the same thing, which both tell me that what? B is equal to c. And then finally, this last term tells me the same thing as the first term. So I have 2a times d is equal to 0, which again means that d is also equal to 0. Let me check this. Oh, sorry, this should be positive. In positive. It's positive because again, I have a over 2 minus then that, which is then a, but then this negative makes it positive. Sorry, so those should be positives. Good. Which actually tells me that b is equal to negative c, not positive c. There we go. Sorry about that. Guys doing okay? So from here, this says that b is then equal to negative c. And then again, normalization says that this guy squared plus this guy squared must then be equal to what? 1. But then since this guy is equal to this guy, then I have 2 times this guy squared is equal to 1, which means then that b is equal to minus c, which is equal to 1 over the square root of 2. This comes from the normalization. So putting these together, what this says then is that the eigenstates corresponding for the energy equal to negative 3a over 2 then corresponds to 1 over the square root of 2 times. So in this case, b corresponded to 2. So this is 2 minus 3 And this is then equal to the 1 over the square root of 2. So 2 then was equal to what? The z minus z states minus then minus z plus z. So this is the eigenstates for this particular energy level, which again is the non-degenerate one. Guys doing okay?
And could you go back one slide just real quick, Professor?
Sure.
Okay. So B is equal to minus C is 1 over square root. Okay, that was all I needed.
Okay. Good. You doing okay, Clayton?
Yeah, I'm good.
Good. Okay. So good. So now let's do the same thing now for, let me use a different color. Is that like using different colors? Good. So let's look at for now the threefold degenerate one, which is when I have a over 2. Right? So good. So my first equation then becomes what? So I have an a over 2 minus a over 2 times a is equal to 0, which means that this gives me a 0 times a is equal to 0, which doesn't tell me anything about a. So a can be basically anything. Okay. Good. So let's look at the second one. So the second one then says, let's go back. Second one then is I have an a over 2 plus an a over 2. So this is simply a with a negative sign. So I get negative a times b plus a times c. And this one tells me basically the same thing. So for these, I then get an a times b minus an a times c is equal to 0, which then tells me that b is equal to c. Okay. And then finally, the last term is the same thing as the first term. So I get a 0 times d is equal to 0, which again doesn't tell me anything about d. So basically, in this case, I have 2 free parameters, right? So 2 free parameters. Those 2 free parameters are that a can be anything and d, right? These are my 2 free parameters. So a and d, but technically b and c are also free parameters because all I am restricted to is that b has to be equal to c, which means that technically I have one other free parameter. So one other free parameter, which again is that b must just be equal to c. Right? Now, if b is equal to c, normalization says that this has to be equal to 1 over the square root of 2. But it doesn't just have to be 1 over the square root of 2. It can also be 0 at the same time. Okay. So basically, putting these things together, since I have 2 free parameters here, one choice is I can choose that a is equal to 1, d is equal to 0, b and c are both equal to 0, which is our first choice that we can choose. Right? So our first option is that since a is free, I can choose a is equal to 1, I can choose d is equal to 0, and I can say, well, b is equal to c, which is also equal to 0. Right? So in this case, my one state then is going to be what? The zz, which corresponds to the one state, right? So this is option number 1. So option number 1 then is that this is the energy eigenstate then for the a over 2. Option number 2, so my second option, is I can choose now, well, a is equal to 0, d is equal to 1, and b is equal to c, which is then equal to 0. So that one then corresponds to the minus z equal to the 4 states, right? So this is then my second, right? So this is energy eigenstate number 1. This is energy eigenstate number 2. The last choice I can make, or option number 3, is now I can choose, what happened? I hate it when that thing jumps. Okay, so I can choose that a is equal to d, which is equal to 0, and then b is equal to c, which is equal to 1 over the square root of 2 from normalization. So in this case, my third possibility is I have 1 over the square root of 2 times then the 2 states plus then the 3 states, which is then equal to 1 over the square root of 2 times then, so the z minus z states plus the minus z states. Right? So this is then the third energy eigenstates. Okay. So let's put all that together here. So basically my 4 energy eigenstates are, so again, the one that corresponds to energy equal to minus 3a over 2. That corresponds to the state 1 over the square root of 2, right in this. So z minus z minus z, z. Okay, so that's the first. For the energy then equal to a over 2, I now have 3 states. The one state is simply the z states. The second state then is the minus z states. And the last state is the 1 over square root of 2, z minus z plus minus z. Okay. So this state up here, this is what we usually call the singlet states, because there's one state where this guy is actually now the true ground state. So this is now the true ground state energy. So basically what's kind of nice about this is if you look at the hydrogen atom, which we'll talk about near the end of the semester, the ground state energy, when you don't take any of these corrections into account, is actually 4-fold degenerate. So the energy for the hydrogen atom without any corrections for the ground state is actually 4-fold degenerate. But by taking this hyperfine splitting into account, you've now broken that degeneracy and now made it a true ground state because it's not degenerate anymore. But now these 3 guys, these are what's known as the triplet states. These guys all correspond to the same energy, but since there's 3 of them, then this thing is now 3-fold degenerate. So it's called triplet because it's 3-fold degenerates. Now, what'll happen is when I have my hydrogen atom make a transition from this state to this state, or from this state back to this state, either one, what'll happen then is I'm going to give off a photon. That photon then has an energy, h bar times nu, which is then equal to twice of A, which turns out to be 1,420 megahertz is the frequency. So this is equal to nu, which corresponds to a wavelength, which is actually equal to 21 centimeters. So 21 centimeter emission is actually a big thing in astronomy and cosmology. So basically, if you have a gas, and that gas is mostly made out of hydrogen, then you can gain information about redshift and distances and all that different stuff, because you know the transitions that this thing is going to make with inside of the gas have to give off photons, where those photons have 21 centimeters worth of wavelength. But if you measure it to be different than 21 centimeters, that will then tell you the redshift of the photon as it has come from that gas cloud to the Earth. Right? So this is the Earth. So different ways that you can have a redshift is because if this cloud was moving, for example, if it's moving away, it's going to be shifted downward. If it's going to be moving toward, it's going to be shifted upward. Not to mention the distance. So the further it is away, the photon has to travel further distance. The universe expands. As the universe expands, it then decreases the wavelength, then decreases the energy of the photon, which basically means that it would increase the wavelength. There we go. Decreasing the energy. So in that case, you also get a secondary redshift. So you get a cosmological redshift due to the universe expanding, but you also get a Doppler redshift due to the gas cloud either moving toward or away. So 21 centimeter astronomy is actually something that's pretty coveted. The problem with 21 centimeter astronomy, though, is you can't do it on the surface of the Earth. Basically because everything else is going to drown out that photon. So basically all the electronics and everything that are giving off light and doing all that stuff is basically going to drown out that 21 centimeter. So to really do 21 centimeter astronomy, you would have to put telescopes on the moon, more precisely, basically on the backside of the moon, the dark side of the moon, where in that case, you're not drowning out that signal again from basically other stuff. But this is the 21 centimeter transition that you have, and that's between the true ground states or the singlet states, and then the excited states, which are then the triplet states, due again to this hyperfine splitting, which again comes down to the fact that you have the proton and the electron both carry magnetic moments. And then it's the interaction again between these magnetic moments that gives this hyperfine splitting. Guys doing okay?
I think so.
Okay, you're being so quiet. Okay. Good. So let's discuss what's happening a little bit further. Okay. So even though we actually saw this, what we're really seeing then are what? Eigenstates of the 2s1 dotted with the s2, right? So what we're basically looking at are eigenstates of this. And to make it a little bit more clear, what we're really looking at is how do we actually add angular momentum? So what we're looking at is how do we add angular momentum for multiple particles? So this is actually what's known as the addition of angular momentum. So let's say, and this doesn't have to be just for spin 1/2, we can do this for any type, but let's just talk about spin 1/2 for now. So let's say we have two particles. Here's one particle, which has spin 1/2. So S is 1/2. I have a second particle. Let's call this particle 1, particle 2, which also has, so spin 1, spin 2 equal to 1/2. And let's say what I want to do is rotate each one of these guys about some n axis. So let's say this is my n axis. So let's call that the n hat axis. This is my n hat axis. There we go. And I want to rotate this to some small angle d theta. So I'm going to rotate each one of these by the same amount about this angle theta. So as we talked about before, to do this, we'd have to use a rotation matrix or rotation operator. So my rotation operator then, R d theta n hat, would then be equal to 1 minus I times S, where S is what's called the total spin, angular momentum, times n hat times d theta, all divided by h bar. But to achieve this, if I want to rotate both of these the same amount, well, that's the same thing as me rotating this one by an amount of d theta and rotating this one by an amount of d theta simultaneously. So this thing is also equal to the rotation for the first particle by an amount of d theta about the n hat axis, tensor product or direct product then with the rotation of the second particle about, again, the n hat axis by an amount of d theta. I think that's my son running again. Okay, so let's look at this guy. So this guy then is going to be a tensor product between both of these two guys. When I'm done teaching my class.
Why can't I write on there?
Because I'm teaching my class. I have to have a...
How can you write?
Look what you just did.
Can you write that?
You have to use the pen. Now, I'll let you play with it after my class, okay? All right, thank you. While I'm ordering, you can draw something. All right.
Wait.
Huh?
Wait.
No, when I'm done, go. Good. So basically, I have two of these terms, and I have to tensor product to each other, right? So now I have 1 minus I S vector 1 dotted with n d theta over h bar tensor product then. Let me move all of our faces up so I have room. There we go. Okay. No, that's not what I wanted. Good. Times 1 minus I S vector 2 dotted with n hat d theta all divided by h bar. So good. Now let's multiply this guy out. So this is then going to be equal to 1, and then I'm going to get a minus I over h bar times, so I'm going to get a S1 tensor product with the identity from 2 plus identity from 2 or from 1 tensor product then with S2 vector, good, all dotted with n hat d theta, right? If I bring this thing only out to order d theta. So basically, if I compare this guy then with this guy, what this says then is we have what's known as the total spin vector. S is then equal to S1 vector tensor product or direct product with the identity from the second plus then plus the identity from the first tensor product then with the S2 vector. Okay. Good. Now, typically, we're going to write this in simply shorthand notation. I'm just going to write this as S1 plus then S2. But basically, what this is saying then is that what the total intrinsic spin angular momentum is then equal to, well, in this case, I'm taking the spin vector from the first Hilbert space, tensor prodding that with then the identity from the Hilbert space of the second particle. Right. So again, we talked about last time that a direct product basically means that I'm taking one Hilbert space for particle 1 here, pasting it then on top of the second Hilbert space. So in this case, what I'm doing is I'm taking the spin vector from this guy and simply the identity from this one. This one simultaneously is saying, well, now I'm looking at the spin vector from the second one. So I'm going to tensor product that because I need to make it in this case, 4x4 Hilbert space. So I have to tensor that with the identity of the second one. Okay. Or sorry, the identity from the first one. So this is what we call the total spin angular momentum. Okay. So this means that we're basically adding then these angular momentums. But again, since this one lives in one Hilbert space, this lives in another Hilbert space, I have to tensor product these guys together, but I don't do that directly since they're added together. So I have to tensor product that then with the identities from the 2 different vector spaces. Again, typically shorthand notation, I'm simply going to write it this way, just because I don't feel like writing out all these tensor products or direct products, but just know this is actually what we mean. So again, this is the total spin for all the particles involved, in this case, particle 1 and particle 2, where this is then just the spin from the first particle plus then the spin of the second particle. Now, one thing I mentioned earlier is that these also don't have to be spin 1/2 systems. One of them can be a spin 1/2 system. The other one can be a spin 5 system. It doesn't really matter. The size of the 2 spins do not have to be the same for this to actually work as well. So again, just because this is spin 1/2 and this is spin 1/2, that's what we did here, but it doesn't necessarily have to be true. This could be a spin 1/2, this could be a spin 3/2, this could be spin 1, this could be spin 2. It doesn't matter. The size of the spins are irrelevant. Guys doing okay?
I think so.
Now, the other thing we know, I got to move our faces again. There we go. Let's put us back over here. So another thing is, as we mentioned last time, since these guys commute with each other, what that means then is that the components of this spin, the total spin, satisfy then the usual commutation relations. Right? So if I have SI with SJ, these guys then are equal to IH bar epsilon IJK SK. Right? So because these individual spins commute with each other, what this means then is that this total spin vector then satisfies the usual commutation relations. You guys doing okay? Now, what this means is what? That means we can build the total spin vector squared, right, which is then going to be S1 vector plus S2 vector quantity squared, which is then going to be equal to S1 squared Make that a hat. Go. I'll leave it as a vector. Vector hat plus S2 vector hat squared plus then 2 times S1 vector dotted with S2 vector. Now, that means then that this term here is what we already found the eigenvalues for. So for the spin 1/2 system anyways, so if S is equal to 1/2, we just found the eigenvalues for this. And the eigenstates. So that means then that the eigenvalues and the eigenstates for this is also the eigenvalues and eigenstates for this as well. So these eigenvalues here are the eigenvalues for this thing as well. So this has the same eigenvalues and eigenstates. Which will definitely be good for us. Now, also, since this thing satisfies this commutation relation, and since S vector squared commutes then with SZ, where SZ in this case is simply equal to S1Z plus S2Z. What this means then is by what we did previously, I think what, chapter 3 or 4, I changed the chapter number, so I don't remember which chapter it actually was. But what this means then is we can build simultaneous eigenstates from the total spin vector, which means that I can take the total spin vector squared acting onto then SM, and that's going to give me S times S plus 1 times H bar squared times SM, and then SZ acting onto SM is then going to give me M times H bar times the state SM. So we can build simultaneous eigenstates out of these guys. And there's a reason I'm doing all this. It'll make sense in a minute. But you guys doing okay? Give me 1 second. No, I lost it. Okay. You guys doing okay?
Yeah, I think so.
This just goes back to all the stuff that we did before when we built the eigenstates and we came up with the Z's and all that stuff from the fact that we had simultaneous eigenstates because these guys commuted, but these guys individually did not. Right?
Okay.
We're just carrying all that on over to here. So. Good. Okay, so let's go a little bit further. So now, what does this mean about our addition of angular momentum? So how do I know this? What does this mean? And etc. So let's talk about that. So first, let's talk about the expectation value of ZS squared. Let's see what this thing tells me. Okay. So this expectation value then is going to be equal to plus or minus Z times then, again, S1 vector squared plus S2 vector squared plus then 2 times S1 dotted then with S2, right? Times plus or minus Z plus or minus Z. Okay. So let's talk about this term first. So if I act S vector 1 squared then onto what? The state plus or minus Z plus or minus Z. So here, remember this is shorthand notation for saying that this is S1 equal to a half. So if I act this guy out of here, this is the same thing then as S1 times S1 plus 1 times H bar squared times then plus or minus Z plus or minus Z, right? But S1 here is simply equal to a half. So this is the same thing then as 1/2 times 1/2 plus 1 H bar squared times the state plus or minus Z plus or minus Z, which is then equal to what? 3/2. So this is then 3/4 H bar squared plus or minus Z plus or minus Z, right? This make sense?
squared.
I have a feeling that was my son's school calling to tell me bad news. I guess we'll find out. You guys doing okay? What was
maybe.
that? Maybe?
I think so. I said maybe. I think so.
Okay. Now, by the same logic, what that means then is that what? S2 squared gives me exactly the same results, right? So that's also going to be simply 3/4 of h bar squared. Right. And the reason for that is, again, this one is acting directly onto this state, where this one is now acting onto only this state, right? So this is acting on the one portion of this. This one is acting then onto the two portion of this. Right. Guys doing okay? Now, when I use this information here, and I plug that back into here, what's going to happen then is the inner product here is going to cause this to go to 1, this also go to 1, which means then that plus or minus z plus or minus z s squared times then plus or minus z plus or minus z is then going to be what? Equal to, so I'm going to get a 3/4 plus 3/4 plus, now the eigenvalue for this guy, remember this guy had 2 eigenvalues, so this was either the triplet or the singular one, right? So this one was then either equal to, right? So let's put this guy in. So this was either equal to 3/4, or sorry, -3/2 or a/2, right? Good. So this is then going to be plus either equal to 1/2 or -3/2, right? All times h bar squared, depending on which one of the states that I'm looking at. So let's write this out a little bit further. So here I get plus or minus z plus or minus z s squared plus or minus z plus or minus z is then equal to, so I have an h bar squared times 3/4 and 3/4 is then going to be 3/2. And then this is going to be plus either, again, 1/2 or -3/2. Okay. So let's look at the first case. So if we're looking at 4, when this energy was equal to a/2, which corresponds to 1/2 here. So in this case, this inner product, so we're going to as s squared, is then simply equal to 2 times h bar squared. Okay. But remember, this is the same thing as s times s plus 1 times h bar squared. We'll talk about that in just a second. For the other one, so for energy then equal to -3/2. In this case, I get a 3/2 minus a 3/2, which is equal to 0, which means the expectation value for this guy then is equal to 0, which is also then equal to s times s plus 1 times h bar squared. Now, comparing the right-hand side then to the left side, what this means then is for this first state here, s then must be equal to 1, which means that this is a spin 1 particle. Where for this one, if I compare this side to this side, this means s then must be equal to 0, which means that this is a spin 0 particle. Okay. Now, to solidify that just a little bit more, let's look at the z portion. So again, remembering that what sz acting on the state of sm gives me then m times the state, times h bar times sm. So again, let's look at that first values there. Right? So remember that for the triplet state, I either had the zz state, the minus z, this way, minus z states, or we also had the 1 over the square root of 2, z minus z plus minus z, right? So let's think about acting as z onto each one of these. So this sz acting on, say, the state zz is then equal to what? S1z plus S2z acting on the state then zz, right? So I act this guy into here. This guy gives me a 1/2. This one also gives me a 1/2. So this thing is going to be what? Simply h bar times zz. Now if I act as z, now onto the minus z states, this is going to give me a minus 1/2 and a minus 1/2, which is then minus 1. So this gives me minus h bar minus z minus z. And let's look at the last one. So here, what's this one going to give me? So this is going to give me a. So if I do sz acting on that state, so 1 over the square root of 2, z minus z plus minus z, then this is going to give me an h bar over 2 minus h bar over 2. So that's then a minus h bar. This one then is going to give me a what? Also minus h bar. So this is going to give me a minus h bar times that state. So let me just write this as stuff. I don't feel like writing it again. Guys doing okay?
H bar. Can you go back through the reasoning on this last state here, Professor?
Sure.
No, not that one. The one we just did. So you had a h bar from the first one.
Right. So this one I get a 1/2 times h bar, right?
Okay.
Minus 1/2 times h bar. So this one term gives me a minus h bar over 4, right?
That's h bar.
This term also gives me a minus h bar over 4.
Okay. Okay.
I think I might be missing a square root of 2 or something somewhere, but yeah. So if I add those both together, that gives me an h bar over 2 with a negative sign. Yeah, I think I'm maybe missing a term, but basically it gives me the same idea as these. It's kind of the point. Okay, so basically what this says then is that, yeah, so either this one then corresponds to a spin 1 with spin up, this one then corresponds to a spin 1 with spin down, and then this one corresponds to, since this has the positive sign, so this one would also be a, what, spin down, I think? Or would this be spin 0? Let's see here. Let's go back to my states. Is that a plus or minus? Let's see here. Trying to remember now. Yeah, that was a plus. So I get a minus and a minus. Yeah. Okay. So good. So basically putting all these things together. So again, we have that when the energy again was equal to a over 2, what we find is that this corresponds to a spin 1 particle. And it corresponds to a spin 1 particle because we found that S was then equal to what? 1. And simultaneously, as z was either equal to plus or minus h bar, which means that this thing truly is a spin 1 particle. For the other one, we have a 1 over square root of 2 times then z minus z minus a minus z, which means what's going to happen here is this one is a negative, this one's also a negative, but that negative is going to make it a positive, which means that when I take sz acting onto this state, this one gives me a 0. So here, when we look at this one, so when the energy was equal to negative 3a over 2, here I find that S was equal to 0 and M was also equal to 0, which then corresponds directly to a spin 0 particle. You guys doing okay? So good. So let's talk about what all this stuff means. So what this means then, again, is that when I look at the energy, we started off with the ground state energy, E1, but then this hyperfine splitting caused this thing to have a lower energy, or that lower energy then corresponded to E1 minus 3a over 2, where this corresponds to a single state of 1 over the square root of 2 of then z minus z minus z, which now corresponds then to a spin 0 particle. Okay. So basically, the addition of the two angular momentums of the two particles caused this state to split into the singlet state. So again, this is our singlet state, but the singlet state acts as a spin 0 particle. Okay. Simultaneously, I have an excited state, where that excited state corresponds to the energy of E1 plus a over 2, which has the 3 states. But these 3 states then, which is what we call the triplet states, corresponds now to a particle which now has a spin 1. Okay. So basically what that means is that when I take 2 particles, a proton and an electron, each one then has a spin 1/2. So particle spin 2 was equal to 1/2. Particle spin 1 was equal to 1/2. I took these 2 particles, these two, the addition of the angular momentum causes this thing to either sum together to create a spin 0 particle or to create a spin 1 particle. Or in this case, the spin 0 particle, the singlet state, is the true ground state, but then when it goes to the spin up state, it then acts like a spin 1 particle, or not spin up, sorry. When it goes to the excited state, it acts like a spin 1 particle, which then has 3-fold degenerate energies. So there are actually 3 different states that correspond to this guy. So this is what happens when we actually add angular momentum together. So when you add angular momentum together, you can actually then create multiple states, where those multiple states then have different spins. How that's going to happen is going to depend on the types of particles at which you add together. Which basically means that here, again, I'm taking 2 spin 1/2 particles. If I have one is spin up, one is spin down, I add those 2 together, that then gives me a total spin of 0. But I can also have that one is spin up, one is spin up. I can add those 2 together, which now gives me a total spin of 1. I can have one is spin down, one is spin down. I can add those together to now, again, create a total particle, which then has a total spin of 1. So 2 1/2 particles can create a spin 1 particle, but they can also create a spin 0 particle as well. For other combinations, other things are going to happen. So for example, if I had 2 spin 1 particles, 2 spin 1 particles can create then 2 different particles, where one's going to be spin 0, one's going to be spin 2. If I then have, say, a spin 1/2 with a spin 3/2, that's again going to create particles, but those particles are either going to be spin, what, 1? Wait, no, 1/2 and 3/2. Yeah, so spin 1 or spin 2. So by adding these particles together, in the addition of the angular momentum, you then create new particles which now have different types of spin, where those different types of spin is either going to be the addition of the spin or the subtraction of the spin. And then what you get for singlets and triplets and whatever is going to depend on the size of the Hilbert spaces. So again, here we're taking 2 spin 1/2 particles, so two-dimensional Hilbert spaces, adding them together, which gives us a 4-dimensional, which gives us the singlet and then the triplet state. But if I added a spin 1/2, which has 2, to a spin 3/2 that has 4, so now my total dimensional is 6. So now I'm going to basically create 6 different states, right? Because now I have a 6-dimensional Hilbert space. So some of them are going to be, what, spin 1, some of them are going to be spin 2. You'd have to kind of go through the math to figure out how they're going to work, because I don't quite know offhand. But yeah, so this is what we call the addition of angular momentum. All right. Okay, so the addition of these spin states will give you then different spin states, which correspond to, again, the addition or the subtraction of the spin themselves. You guys doing okay?
Yeah, I think so.
Okay, so there are other ways we can come up with these states, but I'll save that for Thursday. We'll discuss these states a little bit more and show other reasons why this thing makes sense. But we only got a few minutes, so I'll skip that and postpone that to Thursday. So remember, Thursday we will be back in person. So we'll have a great time.
When are you gonna be back?
I'm closing now. So I'm saying goodbye. You want to say goodbye?
Bye.
Are you hungry? Yeah.
Mm.
Don't play with the pen. We're not ready to do that yet. Are you cold?
Mm.
Your hands feel cold.
Mm.
Would you leave my pen? Stop it. After.
Can
Go.
you-
What's that?
you need to do it.
Do what?
Why?
Yes, you're gonna draw when I say goodbye to that. Okay. How's the homework going?
I think I've got 4 left. So
Not bad. That's bad. Clayton, how's the homework going?
It's going.
It's going.
I have a 16-page take-home exam for constitutional law, so that's been taking up a little more of my time.
There you go. That makes sense. Gotcha. All right. Speaking of exams, we don't have one this weekend, but we have one the following weekend. Okay.
oh boy.
Just be ready for that one. I posted homework for what, chapter 4, right? Or 6 now? The time evolution stuff.
I'm not quite sure, Professor. I haven't been able to keep track.
Okay.
I got
I'll
confused.
I'll probably post some more homework soon. Either later today or Thursday. I'll let you guys know. So.
Okay.
All right. So otherwise, have a good day, guys. I'll talk to you later. I have a hungry boy that wants to eat pizza and wants to and hopefully not break my pens. So,
Yum, yum, yum.
yum, yum. I know. Remember, we're gonna have it delivered.
We'll see you later, Professor.
Yum, 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 yum.
Okay. All right. I'll talk to you guys later. I'll see you on Thursday.
See you Thursday, Professor.
All right. Bye.